then I propose that we now move forward in our program. And our next speaker is Maria Cruz Alonso from the CSIC Institute in Spain. And she will focus a little bit more on the specific durability aspect of corrosion. So Maria Cruz, the floor is yours.
Thank you. Good afternoon, Maria Cruz Alonso. Thank you for your introduction, Kim. I'm working at the Institute of Construction Science, Eduardo Torroja. I'm involved in durability and mainly in corrosion of reinforcement. And so that is the reason I will focus my presentation today in the aspect of corrosion of reinforcement when we have the situation of crack and what can be the expectancies with regard to self-healing. And before we start with this, I want to thank the very nice presentation from the World Pakistan ESRs that they really very well introduced the problem of durability. That is one of the most important aspects to be covered because it's the most costly in the service life of the structures. So in order to start, I will comment again what is the environmental of concrete interaction of the concrete with the environment. Certainly the concrete is interacting with the environment from the very beginnings. It is located in the structure. And there are many reasons for this interaction, as and parameters like SO3, chlorides penetrating through the concrete, the water, the CO2, the temperature. In any case, these agents, when they introduce into the concrete interaction, cause several damages. Of course, we have here today that this type of interactions have chemical, physical, and mechanical, and in general, all of them they cause mechanical failures. Of course, we have heard about the shrinkage and the cracking generated by Eric Slangen, water permeation that was addressed by Marta Roig. Also, we have problems when we have in an environment with sulfates and a very low temperature. Vanessa explained very well, or acid attack or water leaching. But there are other interactions with the environment, like the concrete reduction of the high alkalinity, carbonation, or the chloride penetration. These two aggressive in general, they don't cause any specific damage in the concrete cover. However, they are very dangerous for the rebar. So that is the reason we are concentrating them concerning rebar corrosion. And I prefer to start making also a review on what can happen in the case of corrosion, and try to make the frame for the study. Of course, we are starting with the situation that our reinforcement is passive in the environment due to this high pH. However, due to the interaction with the environment, aggressive like chlorides or CO2, they will penetrate through the cover and reach in a certain time, depending on the characteristics of this concrete cover, the reinforcement. In the case of decrease of the pH, we have very small anodes and cathodes that cause the initiation of corrosion that extend more generally on the surface of the reinforcement. However, in the case of chlorides, this penetration is generally locates attacks in specific points. So we have very small anodes with regard to the higher cathodes, so that cause higher corrosion rates. But in order to have the frame of all of this, we need to think about the service life model. This service life model that was proposed by Tutti in a thermodynamic way, and that now is adopted by the codes. And our interest is always try to quantify this service life model. We are particularly interested in this, the transport of the aggressive and the propagation of the damage, the initiation of corrosion in this case. But within the initiation period, what we are interested in is in the transport of the aggressive that generally is quantified by diffusion coefficients, and also the initiation of corrosion that is indicates the passivation and the breaking of the passive layer. When we have the chlorides in the system, these chlorides, they reach the rebar surface, but corrosion is not initiated at that moment. That means that it needs to be accumulated at the rebar level until a certain threshold is reached and the corrosion is initiated. In the case of the carbonation of corrosion, the pH has to be decreased below the pH with a passive situation. This is due to the interaction of the CO2 that penetrates through the pores and dissolves in the water and react with the alkaline components in the cement base like portlandite. Progressively, the pH is decreasing, and when it reaches a certain level, corrosion is also initiated. So once we have this frame of the for corrosion of the reinforcement to be addressed, so we need to identify this transport of the aggressive, and we need to have into mind that there is a large variability in the identification of this. This is because there are large parameters influencing that depends on the concrete coverage characteristics and also on the environment. And for the second part, the passivation period, we need to identify the time until corrosion is initiated. And that can be identified depending on the aggressive and the characteristics that take place at the steel concrete interface. To understand better this, the steel concrete interface, I think is this picture from this paper on the One Railing Committee that we identify the different parameters that can be influencing the corrosion initiation of the air voids or the presence of dioxide. But we can see here that the crack is one of the parameters that influence this corrosion initiation. The crack finally is not only a path that for a more rapid penetration of the aggressive that it is, but also is changing the microchemical or micro electrolyte at the rebar level, and so that changes the passive layer and of course the initiation of corrosion. So let us now to move again to the crack, the presence of crack in concrete. As Eric was commenting, the structures, they are designed for cracking. They many often have cracks that we can observe in these pictures. Even these cracks can be healed and sealed along its life or can remain unsealed. How this can be this crack, in particularly this deformation crack when the structure is in the operating condition. Consider we have under tensile, there is a crack that appears and enrich the surface that we can identify as a primary crack. Also, due to these forces, some other cracks like secondary cracks can appear, and also some other can remain inside as internal cracks. Finally, what we have in the surface is a pattern of several cracks, transversal and longitudinal to the reinforcement. These multi-crack conditions we have tried to simulate very well by Pedro Serna in the Resilience Project. We are working together, producing this type of element that has been bending in steel bending points, locating several multi-cracking regions, and the compression region with no cracks, and also the lateral regions with no significant cracking. Analyzing this crack, we have a crack width on the surface depending on the deformation of the element, and depending on the type of concrete, the appearance of this crack is completely different, and also the size. You can see here the length and the distance between them is different and much higher in comparison with one ultra high performance fiber reinforced concrete with a smaller length of cracks and a smaller width. And also we can have regions with much more small crack size. So also we need to take into account the crack depth, because these cracks can penetrate or not through the cover and not be able to reach the reinforcement, penetrate and reach the reinforcement, and even overpass and reach a second level of reinforcement. But how these cracks can influence in the corrosion initiation? Now is the moment to understand what happens with concrete and in the analysis of the transport properties. One of the main parameters to analyze the service life of the structure. We are considering the transport that depends on the concrete cavity and the environment. Doing an analysis of the literature with the chloride transport in different types of concretes, even in situ, we can observe that generally most of less are accumulated in this region, but very high chloride transport in this case, or very low depending on the quality of the concrete. When considering the presence of cracks, although there are no much information on that, still it's clearly that all authors agree that there is a clear increase in the transport of the aggressive, even coming from small cracks, and that exponentially increase when the size increase. And the diffusion coefficient depends on the size of the crack. But can self-healing helps and reduce the transport of the aggressive? Although there are not much information in the literature, and we hope to improve with the SmartKings project, there are some papers that address the autogenous self-healing. And although this is the uncracked situation and this is the cracked situation, after a self-healing process, the authors consider that there is a decrease in the chloride transport. Also, this effect has been observed with autonomous healing that depends on the type of self-healing agent. In this case, was polyurethane. This also was addressed by Neil Develin in his talk, and they also observe a decrease in the chloride transport. So there are preliminary results that indicates that self-healing can contribute and enhance the durability of crack structures. For the initiation of corrosion, we need to deal with the moment that corrosion is initiated, so the depassivation moment. So we need to characterize the rebar and use electrochemical techniques to identify when the corrosion is initiated, either corrosion rate or corrosion potential. So to remind again, we are in this situation, the aggressive is reaching the reinforcement, but now what we need is that the accumulation of this aggressive until the corrosion is initiated. This is what we identify as chloride threshold. Some results, for instance, showing here, these are from the PhD of Mercedes Jimenez within the residence project. Here we have considered a high performance concrete. A high performance concrete that has been previously exposed to a deformation, a different deformation level, and we can observe when exposed to the chloride penetration that the corrosion is initiated in different moments. And this is the corrosion rate, and I have highlighted here when it's passive and when it's active. And we have noticed that with the different deformation level, the corrosion is initiated easier and shorter. If we compare this corrosion rate with the crack size, we observe that the corrosion level has been or the corrosion initiation has been overcharged in all the cases with this concrete. What happens in reality? We can have small cracks. This crack can be healed, are observed here. However, the corrosion has been initiated. So we are not enough to support and to protect the reinforcement. With higher deformation, the crack is higher, and we can have some healed cracks, but some other will be unhealed. And finally, the corrosion is initiated. This is before, and this is after exposure. But what can be the influence on the type of concrete? Here we are analyzing the high performance concrete and the ultra high performance fiber reinforced concrete, containing in this case also crystalline admixture and nanocellulose. While the high performance concrete initiates corrosion, and of course it has higher crack size, due to a type of concrete, the ultra high performance fiber reinforced concrete has not initiated corrosion, even for a crack size at the surface close to 100 micrometers. What we observe in this case with the HPC with 1.5 deformation, this is the initial, but after a period exposed to the environment, there are some cracks that are unhealed, but some others are not healed, so the corrosion was initiated. In the ultra high performance concrete, we have a different pattern of cracks, different size, and some of them are healed, and even having some unhealed cracks, corrosion has not been initiated yet. Different reasons can be contributing to this performance. This is the initial, and this is after the healing. But we have another aspect that we need to analyze in the corrosion initiation, that is the crack depth. This is the specimen exposed to the chloride environment, and the chlorides penetrates to reach the 2 levels of reinforcement. In this case, whatever you are in the first or in the second, the corrosion has been initiated at practically the same time, and the crack is relatively high. So probably the situation that we have here is that the crack penetrates not only the first level of rebar, but also the second level of reinforcement. When we have the ultra high performance fiber reinforced concrete, however, the situation is significantly improved, and after a similar period of time of exposure, the corrosion is far to be initiated, further even in the case of the second level of reinforcement. What could be the situation here? That the cracks are very thin and are healed, and even if they reach to the reinforcement, the corrosion was not possible to be initiated, or the cracks are not penetrating completely to the rebar level, and so they are healed, but the corrosion is not initiated. But now we need another parameter, that is the chloride threshold. The chloride threshold, we are thinking in the moment of the passivation, and to determine this time to the passivation. So we identify for that the amount of chloride that we need to initiate corrosion. Analyzing the literature data, we observe that there is a large variability, as I commented, that this is mainly in the level of 0.8, the percentage of total chloride to initiate corrosion. Although the standards, they consider that the value of 0.4 for new structures, and in some standards, they consider the value of 0.6 when they are thinking in service life for corrosion initiation. There are very few data on this case, and there are some of them that indicates really a clear decrease in chlorides to corrosion initiation. So when analyzing the service life of crack structures, we need to think that there is not only a higher transport of the chloride, but also we have a decrease in the chloride threshold. As I mentioned before, the environment around the reinforcement in the crack is clearly changed, and can be the reason for the faster initiation. But now we need to comment something about cancel healing contribute to enhance durability of concrete. I think we have seen like this picture in very different frames and presentations, but in this case we are representing how the structure is evolving with time. When we don't have any preventing action, the structure, there is one moment that is reached the durability limit state, and there is needed a repair. And when it reaches again the durability limit, again a repair. This is causing, of course, an increase of cost of the structure. So what is the durability strategy that we are interested in? We are interested in a non-active maintenance for long-lasting service life. So introducing self-responsive capacities in the structures of predictive, preventive, or corrective functions can help us. This was the idea of this workshop within the Lorthenins project. For preventing action, we can predict the evolution of the structure, monitoring the structure using sensors or using self-sensing additives are were mentioned also here in this workshop. But also we can introduce additives to resist the aggressive self-curing system of cell protection. The idea is that to extend the service life of the structure. And also we can introduce what is identified as latent corrective action, that is self-healing systems. The idea is that the structure itself tries to repair and to recover to extend the service life. How to introduce this in move to the case of self-healing with regard to reinforcement and durability? What could happen if the environment interaction takes place simultaneously with the location of the structure? Of course, we have this element with the reinforcement, and if in our structure we have cracks, we can expect that. And this crack, through this element, the environment is interacting. The chloride is penetrating and reaching the rebar through these cracks, and then the corrosion will be initiated. However, we have a phenomena of self-healing of the crack. The self-healing could be that only partially cover the crack, and then it's impossible to avoid completely the initiation of corrosion. It could be that there is a self-healing of the crack. However, that self-healing is not able to avoid the penetration of the aggressive, and finally the corrosion is initiated. Marta Roche was showing also some real response in this direction. Or we can have a sealing of from the surface, but this could be not enough to penetrate, to avoid the penetration of the aggressive, and finally the corrosion to be initiated. However, it could be a very challenge aspect, and the most interesting one, that is the self-healing of the crack is dense enough to avoid the penetration of the aggressive, and the kinetic will be fast enough to allow the self-healing of the crack before the aggressive will penetrate to the rebar and initiate corrosion. In the case of carbonation, we can have a very similar performance. Carbonation, if in the atmosphere, is low kinetic, low moisture, and the pH drops, and also the corrosion initiates, but as we commented, is more general, extended on the surface. We can have a similar problem when we are thinking in to avoid the corrosion initiation at the rebar level if the self-healing of the cracks is allowed. To finalize, I want to analyze them through this experience and analysis. What are the parameters that could be influencing the crack healing versus the rebar corrosion? We have concrete characteristics that influence in the performance, that is the concrete composition, the cement, the concrete type, the strength, the pore structure, the fiber reinforcement of the concrete. Of course, the crack width and the crack depth. We have the environmental influence. The type of aggressive is not the same if we are in a chloride environment or we are in a carbonation environment, as many aggressive, or the combination of both. The temperature, of course, can influence, and the moisture significantly in the case of corrosion. And what about the crack healing characteristics? The crack healing that depends on the crack healing rate and the capacity to heal the crack healing kinetic, the crack healing density, the crack healing penetration. We have different observed and presented today different cases where we can have a surface self-sealing, however not a complete self-healing inside the cracks, and not be able to protect completely the crack. So clearly what we are not interested in is that we have a crack, and if there is not a heal process of this crack, clearly the rebar is not protected and the corrosion will be initiated. However, we can have a heal process of the crack, but this healing is not enough to protect the reinforcement, and the corrosion is again initiated. However, we can have a final step, and that is the challenge of the smarting and the self-healing with regard to corrosion, that although we have a crack, this cracking will be healed in such a way that is able to protect the reinforcement, and corrosion will not be an issue. Thank you for your attention. I want to thank the Resilience Project that gave us the opportunity to make this experimental study, and also my colleagues, Mercedes Jimenez and Pedro Serra.
Thank you, Maria Cruz, for your very nice presentation. Clearly, some challenges remain in the future work. What I was wondering, if we are looking at self-healing concrete, what do you think would be the most important aspects that we tackle? What is the most important parameter for the chloride ingress in cracked concrete? Is it then the crack depth or the crack width?
Probably both, but it depends on the type of concrete. The type of concrete is significantly influencing in that, the crack pattern and the crack size, and also the crack width. Of course, is most of the studies indicate that the crack width has a significant influence, and the crack depth, of course, is relevant because that could penetrate to different levels of the reinforcement, and that is a more dangerous situation. But if the crack is decreasing in width, as the crack is penetrating, of course, part of this crack could be healed and allows a certain retarded in the initiation of corrosion of the second level of reinforcement. But anyway, we need to demonstrate and work more on that. Still, there are not enough data on this. Clearly, smarting the transport of chlorides is one aspect that will be probably addressed by most of the ESRs, and even probably in some other cases. So we hope to finally, with this project, to get a very huge amount of data, of information to answer some of the questions that we have now.
Okay, thank you very much, Maria Cruz.